Well, good afternoon. Good afternoon. Good afternoon. There it is. Thanks, Paul. Good afternoon, everyone. My name is Blake. I'm a co-founder, president, and CTO at Essentium and Trifusion Devices, a biomedical device company. We're here today to talk about electrostatic discharge and EMI shielding applications in conjunction with Essentium's flash fuse technology, unlocking very interesting potential for electrical applications using FDM additive. So today, again, game-changing electrical opportunities, and you'll see why I'm using these sort of big, fluffy, superlative words here in a few minutes. I'm going to start, though, by kind of outlining the problem facing FDM. Why has FDM been limited in its industrial application, and what are we doing to solve that? I'll talk about the flash fuse process as part of that solution. And then we're going to really get into the heart of this thing. ESD, we're going to go over a little bit of background, how we see the problem, and some use cases, as well as applications that we are looking at. And I'll finish it up by, again, just kind of fleshing out a little bit more of who Essentium is, how can you interact with us, and what are we doing in the additive space. So I'm going to start off by kind of posing a question. This is one we get a lot. So is FDM or FFF, is that a viable industrial process? There's a lot of folks that sort of say no. FDM is great for Yoda heads, Eiffel Towers, toys, trinkets, but really is it useful for industrial process? And if the answer is yes, is it going to cost me an arm and a leg? The answer is yes, it's useful, and no, it doesn't have to cost too much. So how do we prove that it's useful, and what are the advantages of FDM? We've kind of ranked a few different of the primary industrial 3D printing technologies on spectrum from not great to great. So we look at FDM, SLA, and SLS. There's other technologies out there, and a lot of them are really great. These are the big ones, especially in the polymer space, and so that's what we're going to talk about today. So let's start off with uniformity. When I talk about uniformity, I'm talking about whole part uniformity, right? You can start out with a really strong, incredible material like carbon fiber filled polymers, but if that joint's not very strong, am I still on? If that joint's not very strong, then it almost doesn't matter how strong the base material is, right? Because your part is not very uniform. These other technologies have gotten a lot more advanced in their ability to produce a more uniform part. I'm not going to call it an isotropic part because it's not, but it's more uniform. So then there's a host of kind of other metrics that the industrial user really cares about. Everything from strength of the raw material through to improved resolution, multimodality materials, build speed, and print size. So I've ranked the technologies as kind of our worldview, right? This is how we look at the additive manufacturing world. So, FDM's pretty good on a lot of those. If only we could get that uniformity up, then I could print structural parts. I could print engineering grade parts with engineering polymers that are used in injection molding and other processes with FDM additive. And wouldn't that be nice? So for us, functional strength means isotropic parts in the whole part. And I'll tell you how we're able to do that and what it also means for ESD and EMI. But to start off, what I'm going to do is I'm going to show you a little video of flash fuse, what flash fuse is and how it works. And that'll explain how it's possible with fused filament fabrication.
History has always been driven by invention. From the making of fire and the design of the wheel, to the Gutenberg press and the cotton gin. From Thomas Edison's light bulb and the Wright brothers' first flight, all the way to the miracle of landing on the moon. None of it could have happened without imagination, a good amount of courage, and the belief that things can be better, that nothing is impossible. The greatest inventions to transform the world didn't just happen overnight. They each suffered through thousands of failures, mistakes, and missteps. Until that one day when somehow the magic happens. Edison finds the right design of an incandescent bulb. The Wright brothers found the perfect balance to control an aircraft, and a new world of possibilities was born. Today, we stand on the cusp of the next industrial revolution, driven by the invention of 3D printing.
In the world of 3D printing and manufacturing, we've got our own set of obstacles to face. One of them is structural strength. With 3D printing, you're laying down thousands of layers of material. Often with more complicated designs, inner layer strength just plummets. Until we solve this problem, 3D printing is doomed to remain relegated to weak prototypes and trinkets like Yoda heads and Eiffel Towers. Well, we've got some good news. We've discovered a way to combine the ease and efficiency of three-dimensional printing with the power and strength of leading-edge technology. Introducing FuseBox.
Well, I have a wonderful electronic invention I want you to see. It looks something like this.
So how's it work? Well, it's a two-step process. First, we coat the filament with a thin layer of highly conductive carbon nanomaterials. Next, using our patented flash fuse technology, we use electromagnetic waves to excite the particles in that thin layer, causing the layers to react and heat up rapidly. This heating allows the layers to weld together. So what does this mean? We now have the ability to weld an entire printed part together during the printing process, achieving up to 98% the strength of an injection molded part. No post-processing, you take the part off the printer and it's ready. We provide a new level of strength never found in a 3D printed part before. Isotropic properties comparable to those in injection molded parts. The uses of our product are game changers for the automotive, aerospace, medical, defense, and petroleum industries, all of which depend on practical parts that must be used in production. The future is here. The possibilities are endless. So let the revolution begin.
All right, so now that you've seen it in kind of graphical form, how does it really work? That's probably the next question. Again, we're addressing kind of this age-old problem facing FDM printing. And that is, particularly under fatigue or impact loads, those poor interlayer bonds don't produce a strong enough weld in between all those layers. So again, this has limited the application for FDM additive, and it hasn't been able to really achieve the potential offered by the materials that FDM additive can really capitalize on. So our solution is a two-part solution. One, we start out with a whole lot of material science. We make those materials electrically conductive, which allows the ESD and EMI shielding applications, and also provides the fundamental underpinning for the mechanical property improvement. And then we add that FuseBox technology. It's just like a chipset that goes into a computer. The FuseBox goes into the printer, and it unlocks that mechanical welding capability. So let's start with the materials. We take monofilament, kind of in the upper right-hand corner. We coat it with a carbon nanomaterial composite coating. The polymer matrix is the same as the base polymer. And then we 3D print a part, and so you're looking at a nozzle cutaway here. And so the polymer just goes through extensional flow, and you don't get a lot of mixing in between the outer layer and the polymer core. So this is really important for two reasons. Number one, all the mechanical properties that you sort of have in this core here, whether it's just neat, unfilled resin, or even carbon fiber or glass fiber filled polymers, all those mechanical properties are maintained. They're not interrupted by nanotubes. And then the second thing that's really great about that is it keeps your costs down, because all the expensive materials, the carbon nanomaterials, they're just used on the outside in a very thin film. So then you can see, even from very small parts, when you take a cross-sectional view, we do not get mixing. So our carbon nanotube composite stays highly segregated from the inner core of that plastic filament. And then while we're printing the part, again, you're building the part up layer by layer, trace by trace, just like a conventional FDM process. But these polymer chains, they were formerly just resting on top of each other because they didn't have the thermal energy to entangle. Now they got the thermal energy right at the interface so that they can cross that layer boundary and entangle. This promotes interlayer strength, dramatically increasing the whole part isotropic properties. And here's the secret sauce. This is why this works. This is why this is special. Because our electrical conductivity is 1 billion times higher than the next closest commercially available electrically conductive filament. Let me say that again. We're 9 orders of magnitude more electrically conductive than the next closest conductive polymer that's available on the market. We've used 4-point probe tests, we've measured printed parts, we've measured filament, and this is why our technology works, because the electrical conductivity is so much higher. So what does that mean for mechanical properties? What we look at is we look at the mechanical properties in between the joint from a fracture toughness standpoint. So when you look at bulk polymer, you basically sort of have fracture toughness right in this range. 3D printed parts, the fracture toughness dips quite a lot because you have that really poor weld. And then with our local process of introducing the heat at the joint, we actually get not only improved fracture toughness, we get a taffy type failure. So you get increased ductility, increased strain at break, and a dramatic improvement in the whole part isotropic properties. And then when you're done having fun in the lab, you can just hang out a little bit on a 3D printed part that's printed on a chain link and stretched in that Z direction, because you know you're not going to fall on your behind if you go out in that hallway there. So what materials can be used in the process? This is where this gets exciting, guys. It's not just one material. It's not just 6. It's not just a couple. It's an entire spectrum. If you go across the right-hand side here, you're looking from left to right at mechanical properties increasing. If you look here at usage temp, you've got usage temp, 60C, 100C, 200C, and beyond. So our process works with any thermoplastic polymer because the physics translate. So we've got polymers we're working on that are urethane, elastomeric polymers, and sort of 80 and 90 Shore A, 64D, and a really cool flame retardant grade that's already been aerospace cert. And then we've got copolyesters and kind of natural, polyesters and stuff in this class, styrenics and polyamides, all the way out to glass fiber, carbon fiber filled, polycarbonate and polyamide. And then you start getting into your exotic materials. This is where it gets interesting. PEEK, PEI, PESU, PPS, all those materials, and they can be carbon fiber filled and then carbon nanotube coated, and the entire part can be so much stronger than ever was possible in the past. The two materials we're launching with are polyamide. It's a really nice ultramid material from BASF, and an engineering grade PLA that can be heat treatable and used widely in a whole lot of printers at fairly low cost. So check out these mechanical properties for exotic materials and carbon fiber infused. You got PEEK, PESU, PEI, and you can start to have access to tremendously high mechanical properties. And by promoting the part isotropic conditions, then a whole new realm of metal replacements is absolutely possible using this technology. So once we start looking at ways to dramatically improve the uniformity of the materials, then FDM starts to become interesting and competitive, if not exceeding, other 3D printing technologies. And in addition, our build speeds can increase because we're preheating, heating with the layer of filament, and we're post-heating with that plasma-based system. So use cases. Let's talk about what this means for electrostatic discharge and electromagnetic interference shielding cases. So first of all, let's talk about what causes ESD events. ESD events are caused by dielectric breakdown, right? Either in the air or in the polymer or in whatever that material is that comes in contact with an area of charge buildup. This can happen when you're walking on the carpet, when you're walking across the floor. You can actually build up charge on your body in the kilovolt range, which is quite a lot of charge. So that's why that shock event can be harmful to you, it can be harmful to electronic components, it can be harmful to machines, and you really have to have a dissipative material used in many applications to try to prevent this accidental discharge across the dielectric. So Faraday cages, I mean, you've got a guy, I'm not sure that I would stand inside that Faraday cage, but this gentleman is really, really trusting his Faraday cage. All you have to do is build up that conductive material that can have contact at first with your conducting event to dissipate the electrical charges even at really, really, really high voltages. So ESD is governed by kind of like Ohms Wheels, so you have a whole lot of equations. You guys perhaps know this better than I do. I'm a material science guy, really at the heart. But the point is, we've looked at ways that charge can be built up and how it needs to be dissipated, and the fact is that our electrically conductive materials can dissipate that charge so much more efficiently than any other electrostatic polymer that we've ever seen. Applications would include, outside of just ESD and dissipated ones, anechoic foam chambers, and then there's polymer coatings that are used widely in aircraft applications and other applications. And this is all kind of an interesting use case when you start to be able to apply that polymer and weld it to itself and potentially as well to other structures. Radar absorbing materials, again, it would be nice to make parts that could become invisible to other machines. And so machines can detect each other by using radar. So if you can make that invisible, that's useful. These are some examples of radar antenna designs and other impact factors and mechanical structures that if they could be 3D printed with a dissipative material, then new design freedoms and packaging solutions are really widely available. And you can eliminate fasteners by miniaturizing chambers and miniaturizing other structures to really promote efficient designs. Electromagnetic shielding is really interesting. Have you guys seen the videos from these Russian guys that are shooting with microwave guns? They were actually able to disable a vehicle on the road because they shot a microwave signal out and burned up some of the electronics inside the vehicle. So maybe there's applications where you'd really like to prevent long-range incidents from other electric signals, and that might be of interest. So let's talk about electroplating for a minute too. Since our materials are so conductive, you don't actually need to do any other post-processing step before you're ready to apply electroplating to printed parts made with our materials. In fact, we've shown that both for filament and for printed parts, you can electroplate with copper and a variety of other materials very easily. So let's talk also a use case here mechanically for injection mold components in automotive. We got the question, can I make a tooling application for a prototype tooling and make that relevant using 3D printed tooling? The answer is of course yes, and here's some of the value props. We can cut the lead time down by a factor of 5. We can improve the cycle time by designing cooling chambers now that are more circulatory in nature instead of gun drills with casting cores at 90-degree angles and other things you have to do with subtractive manufacturing techniques. And for small run parts that need Class A finish, incorporating in additive and then subtractive workflow makes a ton of sense. So what we did was 3D printed a near net preformed shape. This is a big part, 24 inches by 10 by 8. And it was an 8 kilogram part, 100% infill. And we're looking for 100 shots useful life. So this is for a prototype application or a short run part, something of that nature. And really the competition here is like an aluminum tool. So if we can displace what would otherwise be a conventionally machined aluminum tool, then that's a huge opportunity for additive. So we took that preform, we put it on a CNC mill, cut off the first, 1 or 2 layers just to kind of get down to that Class A finish. Use the same kind of machining parameters as you do for aluminum. The exact same machining parameters. And we got a really nice Class A finish on this thing. Then we put it in a 450-ton press in Detroit and you mounted it up, you can see it in the press there, and got injection mold shots right off the tool. So this is an exciting application. We're still developing it. We're looking for other partners who are interested in this as well. And we see a really bright future for tooling applications with this flash fuse technology. So a bit about Essentium. Who is this little company and what are they doing in this booth and at this show? Our company started out about 3 years ago, I guess nearly 4 years ago now, with really an injection molding focus, so polymer composites, biomaterials, and biocomposites focus. We got awarded an NSF SBIR Phase 1 when I was going through grad school, and then we started to productize. So we said, hey, we can make filament for 3D printing. And we also started to at that point onboard new technologies to make 3D printing much better. We got a Phase 2 awards. We started messing with molecules a little bit, where we do reactive chemistries and reactive extrusion in the barrel of the extruder. And then at the same time also began to launch precision filament for the industrial and biomedical customer. Along that same period of time, we launched another company called Trifusion Devices that makes 100% custom, additively manufactured structural prosthetic parts. So prosthetic sockets, and we started it separately and then we rolled it up into Essentium. So we've been in the additive space for about 1.5 years, working really on getting this flash fuse technology commercialized. Essentium Materials is a vertically integrated company with manufacturing, analysis, mechanical property design, and final component manufacture. We're in College Station, Texas, a short hop away from the rest of the country. So team started out fairly small, and now we're at about 30 people. We're scaling rapidly and excited to launch flash fuse technology here at this trade show. So if you're asking how can you be a part of this thing, we're taking pre-orders now. We have 2 3D printer companies with whom we're integrating this technology right here on the show floor. Stop by booth 1313 if you hadn't had a chance yet. Check out our plasma in real life. You can see it, hear it, and smell it because it's plasma. And Stacker 3D and Aeon 3D are both of our launch partners, and the entire system price is below $25K. So there's options for you to integrate this solution in with your either R&D or manufacturing needs at very accessible price points. The other thing we're doing is we're catching a lot of voice of the customer right now. So let us know what's important to you. What applications are of interest? What questions? What materials? If we don't have a material on that chart that you're interested in, let us know what that material needs to be. If you've got a dielectric property or dielectric constant that you're really interested in, let us know what that is, and we'll be glad to work with you to make sure there's a material to meet your needs. So with that, there's some references for the ESD applications, and glad to answer and entertain any questions that you have at this point in time. Thank you.
That was a great talk. That was a great talk. I had a question about the process of coating your filaments, where that happens in the process. Is it during the creation of the filament, and how exactly do you do that? Just a little curious.
Yeah, our filament is prepared in line. So we manufacture the filament where it has the carbon nanocomposite coating on the outside, all in line. And then our filament, after it's coated, it then goes through our laser gauge system. So it still has the same industry size and ovality specs as monofilament that's available elsewhere. It's such a thin film coating too that you don't see nozzle jams, you don't see accelerated wear really on the tool head any more than you would with carbon fiber filled, for example. We've printed thousands of hours with multi-layered filament, and you're still going to get jams, but no greater than you would with other types of filament. So it comes down to the user being comfortable with the material and understand how it works, and we're here to help you with that for sure. So, yeah.
So during the fusing process after it's printed, does the carbon coating burn off, or is it still on the filament? And if it is still on the filament, does that not kind of create a composite material on its own at that point? I know it's a low loading, but would that not change the properties at that point?
The carbon nanomaterials stay. They don't burn off. It would take a lot of energy to degrade or create char, any of those things. Yeah, we make sure that we keep like the temperature of the printed part at the critical sintering temperature, so below the melting temp, above the TG, so that we can promote that polymer chain mobility without degrading the polymer, causing shifting or warping of the printed part. It remains dimensionally stable, right? Because the inner part of the filament is either agnostic to the presence of the electric fields or so much lower in terms of its coupling than the coating that it's as if it's not even there. Does that answer your question a little bit? Okay. No, there's no degradation. You have a question, I could tell.
Do you have any problems with like flaking of the carbon nanotubes on the, like, do you have to be really careful about how you handle the filament once it's been coated?
No. I mean, it's a good question. So since we apply the coating it's basically a carbon nanocomposite, like a nanotube composite master batch itself. The carbon nanotubes are totally encapsulated by the polymer, and so it's a polymer nanotube outer layer. It's not a nanotube outer layer. Yeah, you'd certainly be worried if it was like a solvent bath, or if it was some other like electrostatic interaction, or if it was sprayed on. But since we use a nanotube polymer master batch outer layer, the nanotubes just stay in the polymer. Good question.
So when you do the fusion, when you print the first layer and then the second layer and then multiple layers, does the previous layers still get constantly heated after, you know?
Good question. No, what we've done to create the electrical circuit with the 3D printed part is we're grounding out through the nozzle. So the circuit, the shortest path for the circuit, the electrically shortest path is basically from the hot end applicator through the part, back out through the nozzle. So in essence, we've moved from what's previously like a point source of heat in the hot filament that was being laid down to a much larger heat affected zone, like 10 to 20x larger, because it's now an annular ring that's applying the plasma. And so your printed part stays hotter. It preheats, it post-heats, and it stays hotter for much, much longer. But it doesn't go all the way back down through to the base layers. What you may also be asking with this question too is, do we worry about resistive growth as the part height increases? No, because we've created a moving ground plane with this solution. So the part is grounding out as the nozzle is moving, as the part is being built. So whether the part's very small or very large, very short or very tall, your conductive pathway stays with the nozzle.
So you have a scanning electrode that's basically following the nozzle, is that right?
The nozzle is the ground part of the circuit, and then the rest of the electrode is attached to the nozzle.
Oh, okay.
Yeah.
Cool.
So it's all attached to the hot end. It's all moving together. Yeah, this allows you to use the same kind of part, like bed materials that you'd like to use, whether it's a PEI sheet or blue painter's tape or glass plate or a metal plate. Doesn't matter. Your removable build plate, totally fine. So.
Hi, thank you so much. It sounds like Essentium's doing some great work in FDM. Do you have any plans to move into any of the other 3D printing families, as far as the other 3D printing technologies, whether that's SLS or SLA or?
Man, there's so many answers to that question. I mean, the first answer is that there's so much that FDM can do. You know, I mean, you can scale from very small parts up to printing cars. You can use soft and floppy materials, or you can use aerospace grade materials. There's some design freedoms that things like SLA may offer in terms of lattice geometries that are interesting. The physics would suggest that nanoparticles inside of liquid resins or nanoparticles inside of micronized powders, in the case of SLS, would also certainly couple with our plasma-based systems. We've ideated a little bit on that, but our primary path is FDM. So, yeah. That's great. Thank you all for coming. Come up and talk to me if you want, or come by the booth. Thank you all so much.